Hello everyone. Welcome to this training about Qualcomm Linux AI developer workflow. I'm Megha Daga. I'm the Senior Director of Product Management at Qualcomm for our IoT business unit. I lead our AI portfolio for the IoT verticals. With that, let's get going. So to begin with, what makes the development of AI applications for IoT devices so important? IoT is one of the most fragmented industry. The smart enablement use cases varies from a smart doorbell in your home ecosystem to a back-end server in a warehouse automation scenario. As the industrial transformation has accelerated with the Industry 4.0 revolution, the requirements have been changing to meet that variety of AI supporting use cases. And as the edge is becoming more sophisticated, innovative technologies from Qualcomm Technologies are here to help these embedded IoT devices meet these next-gen requirements. Then lately, the emergence of generative AI have further extended the possibilities of these use cases in IoT. Therefore, the development of on-device AI has become extremely important. We have been driving the development of on-device AI in creating platforms that make it easy for developers to create their AI solutions for these IoT devices. There are three major pillars that we see making this on-device AI possible. The first and foremost is our hardware. Qualcomm Technologies have been focused on developing the best-in-class hardware. For that, we provide the heterogeneous computing. For AI development, we have resources and IPs composite of CPU, GPU, and NPU that provides this AI acceleration. We are always working on the state-of-the-art models and evolving these IPs to cater to the requirements as these models require. On top of that, the second and the most important pillar for us is the software. Software is where we are making the most investment and making it for our developers as seamless as possible. We believe in a unified software stack, we believe in a modular software stack, and we believe in sticking to the standards. This way, we are able to make sure that our developers can seamlessly deploy their use cases, their applications on our hardware. Last but not the least, the pillar of applications itself. We work extensively in-house and externally with our ecosystem partners to get application development ongoing on our hardware platform using our software ecosystem. By doing that, we are always in the front end of the applications that needs to be deployed for enabling these use cases that we just talked about. By working internally and externally with these state-of-the-art applications, we are able to make sure that our software is always evolving. Our hardware is always able to cater to these kind of applications and use cases and models underneath. So with those three main pillars, Qualcomm Technologies is able to stay on top and forefront of making this AI enablement possible for the use cases that we have been seeing. So with that, let's get into the AI software stack. So AI software stack. As we mentioned, this is our biggest investment and the most important focus from AI development aspect of things. As I said, we believe in a unified, modular, customizable software stack. What that means for us is no matter which tier of chipset you pick from our software, from our hardware ecosystem, you would be able to utilize the same software stack. As you can see, if we go bottoms up on this architecture design, no matter you pick a chipset from the lowest tier to the premium most tier, the AI framework runtimes that we support are unified. We start with the Qualcomm AI Engine Direct, which is our modular APIs that you can use to deploy your applications optimally on any of the underlying hardware cores, be it CPU, GPU, or the NPU. On top of it, we support two major runtimes. We support our homegrown Qualcomm Neural Processing SDK for an optimal deployment, or we work very extensively with the standards and the community out there with the TF Lite runtime. With both those environments, we are able to cater to all the common frameworks which are out there for your model deployment. On top of it, for IoT-specific use cases, where we are looking at an end-to-end application deployment, we provide Qualcomm Intelligent Multimedia SDK. Qualcomm Intelligent Multimedia SDK is a standard GStreamer-based SDK which makes your life simple in putting all these pieces together to create that use case down. And we will be looking at it with few examples later on. With this software stack, what we also provide are the helpful tools. Tools are very important and useful products that are available to you guys for your whole application journey. There are two major tools that I want to highlight over here. AI Model Efficiency Toolkit, which is also called out as AIMET, and AI Hub. AIMET is a toolkit which is provided to our developers to quantize their models, to prune their models, and get to your required accuracy. This is for the advanced developers who want to get to the most optimum performance on our chipsets. And then Qualcomm AI Hub. Qualcomm AI Hub is the latest introduction in our family of tools, and it provides that seamless journey for the developers where you can just take it as a one-stop shop. You can come pick your model from hundreds of pre-trained optimized model from the suite of models that you get on the AI Hub and get going from there and have an optimal performance running on Qualcomm powered devices. So with those software tools and the software stack, we are able to follow through the AI developer workflow. So let's walk through the flow itself. So for a developer, we look through their journey and we split it into two major parts. Step one, where you are getting ready with your model. So let's say you have a use case, and for that very use case, you want to pick a pre-trained model. Once you have picked your pre-trained model, you need to go into the compilation and optimization of a model so that your model is now ready for the Qualcomm supported hardware. For that, we have two different software stacks that are available to you. First one, Qualcomm AI Hub. Qualcomm AI Hub, as we mentioned, it already has set of hundreds of pre-trained model that you can pick and choose from. Once you are happy with the pre-trained model, or if you want to bring your own model, you can do the same too. So in either of the case, once you're happy with the model, you can select the specific device of your choice. You select a device, you pick the model, and then you just get into the test and the validation phase. In this phase, you're actually running your model on the device, and then you can look at your KPIs real time. Once you're satisfied with the KPIs that are in front of you, you have the optimized model ready with you. Or the other way, if you want to go a little bit more DIY approach, you have the Qualcomm AI Stack. In Qualcomm AI Stack, as we saw in the previous slide, you have the neural processing SDKs where you can use them to deploy your models in the efficient and optimized way on the Qualcomm powered chipsets. Once you are now happy with your optimized model, you can go into the next step of building your application. So you started with a use case. You picked a model for that use case, and now we have that use case. Let's say the use case is about a vision AI application where you have camera, you have AI, you have display, all these different components coming into play. And for that, we have the Qualcomm Intelligent Multimedia SDK. It's a standard GStreamer-based SDK. It's a plugin-based approach where you can basically pick in the right plugins, either from the open source community or from Qualcomm optimized plugins that we provide as part of this SDK. You can connect these plugins together, and then this SDK will automatically take care of the pipeline execution, the memory management between those plugins, and getting you the most hardware accelerated performance for your end-to-end use case. So with that, with those two steps, now you're able to have your use case running seamlessly, deploying on the Qualcomm powered chipset. So that's how seamless this journey could be for you. And there are multiple examples that we will be talking through. So with that, let's march to the next section where we will double click into that step one of what we talked about, compilation and optimization of the model with Qualcomm AI Hub.
We have developed the Qualcomm AI Hub to really help you simplify the process of deploying your machine learning models to your edge devices that run on Snapdragon chipsets. You can optimize, validate, and deploy your AI models on your Qualcomm Technologies platform-powered devices within minutes. This makes it incredibly easy to get your AI models onto your devices for use cases such as vision, audio, speech, as well as other machine learning use cases. You can use Qualcomm AI Hub in two ways. You can download and use existing models from Qualcomm AI Hub, or you can bring in your own model to Qualcomm AI Hub optimize it, and then export it, and then use it on your device. Now, we will go through the process of using pre-optimized model directly from Qualcomm AI Hub. First, you can navigate to the Qualcomm AI Hub to access pre-optimized models available for Qualcomm Robotics RB3 Gen 2 platform. Filter models available for the RB3 Gen 2 platform by selecting QCS6490 as the chipset in the left pane. Now, you can select a model from the filtered view to navigate to the model page. On the model page, select QCS6490 from the drop-down list and choose TOTScript to TF Lite path. Click on download, and once downloaded, the pre-optimized model will be ready for deployment. Now, we will look at how we can bring your own model into Qualcomm AI Hub. We are using the YOLO X model in our Qualcomm AI Hub pipeline. First, go to your notebook and you will install the Qualcomm AI Hub package, which uses the name QAI Hub. Then you can verify your API token. You can find the API token from the Qualcomm AI Hub portal. You can copy and paste the API token at the end of the following command. Now, we can get an ONNX model for YOLO X. Once that is downloaded, get this API from Qualcomm AI Hub. It will convert the ONNX model to TF Lite, and then on your chosen hardware, it will run and profile it for you. You will also specify the input shape here, among other things. Once you run this job, you will get links to view the job on Qualcomm AI Hub portal. You can get to the metrics portion of the display and see the metrics for inference time, memory usage, and compute units. Another thing you can do is run the get status API from the Qualcomm AI Hub to check the status of your job. Now we will create a new job and specify the profiling data and TF Lite model to download the profiling information and the target AI model. Once we have downloaded the TF Lite model, we will create an instance of it. Then we come to YOLO X pre-processing pipeline. Now let's go over one of the key Qualcomm AI Hub tasks, which is inferencing. You can run an inference job on your hardware with the submit inference job API. And you can add your device after hub.device. Once you run your inferencing job, you can go to the metrics in your job link and see the inference time and memory usage, as well as your runtime logs. Let's go over the details on Tensorflow Light or TF Lite, which is an open source deep learning framework for on-device inference. TF Lite helps you run your models on mobile, embedded, or edge platforms by optimizing your model for latency, model size, and power consumption. Qualcomm Technologies support executing TF Lite models natively on Qualcomm Linux hardware through TF Lite delegates. We have three options for delegates, depending on the type of hardware acceleration that is needed. The Qualcomm AI Engine Direct delegate can be used with CPU, GPU, and HTP. If you are using CPU hardware accelerator, you can use the XNN pack delegate. For use cases where you want to focus on the GPU, use the GPU delegate. Now we will get into the details of Qualcomm Neural Processing SDK. It is a software accelerator runtime for execution of deep learning neural networks on the device. The Qualcomm Neural Processing SDK takes advantage of the heterogeneous computing capabilities from the three processing engines, the CPU, GPU, and DSP. And the primary focus is on the Qualcomm Hexagon processor. We can use this AI runtime with common AI models, including ONNX, TensorFlow, and PyTorch. The Neural Processing SDK supports offline network conversion tools, which will help you with debugging and optimizing your AI applications. This is great for improving the network performance of your applications. We have also made this AI runtime very developer-friendly. You can easily access the documentation and use the sample code that is offered via the SDK. And the SDK is designed so that you can easily integrate it into your applications. Now we will look at some details on how we take a pre-trained model, then optimize the model, and finally deploy the model on your edge devices. So let's start with the pre-trained model first. First, you will need to port your pre-trained model through DLC conversion, which means converting the model to a deep learning container or DLC file. Then you will quantize your DLC file. The quantization process involves lowering the precision to improve the computational speed, reduce memory usage, and save battery power. Making your AI model more efficient is especially useful for deploying on your edge devices, which may have a lower capacity. After your model is quantized, you can further optimize your model with two processes: accuracy tuning and performance tuning. Accuracy tuning involves refining your model's MAP scores and F1 scores. Performance tuning involves optimizing your model to match the expected throughput and latency requirements for your application. Please refer to the SDK documentation for complete capabilities of using Neural Processing SDK. Some other important capabilities, for instance, include setting up a Docker for your SDK environment. Here are some examples of using Qualcomm Neural Processing SDK. The first step is the conversion. The Qualcomm Neural Processing Engine supports the conversion of models from ONNX frameworks. As you can see in this example, the ONNX model is converted to a DLC. Other supported frameworks include TensorFlow, PyTorch, or Keras, just to name a few. So what does it involve? It involves the input, which is the ONNX network or the ONNX graph. For this example, we are passing a super resolution ONNX graph. And here we are defining an output path where the DLC needs to be. You can refer to the SDK documentation for more details and examples of arguments you can pass. Here you can see you have the framework model. You have the model layers, and now we have the DLC layers, which are the intermediate representation, which can be routed accordingly to the hardware. The DLC conversion is now done. The next step is to quantize the DLC. At a high level, let's cover what quantization means. The GIF example shows the change in accuracy in a photograph when it changes from 24 bits per pixel to 8 bits per pixel, and then finally to 1 bit per pixel. In quantization, we use lower number of bits and thereby reduce the precision, but still retain a sufficient accuracy for our models. For example, we may go from 32-bit precision to an 8-bit precision. The transition from 32-bit to lower bits while retaining accuracy is what we refer to as quantization. There are many benefits to quantization. It helps reduce the power, it lowers the memory bandwidth, it lowers the storage requirement, and it improves the performance. These are all important qualities of developing AI applications. Now, let's talk about how the DLC is quantized. For Qualcomm Neural Processing, the command as we see here will be snappy DLC quantize. First, you pass the DLC, which is the input. Then you pass the input list of sample data for the post-training integer quantization, and then use the adjusted weights. Next, you have the output DLC, which is your quantized DLC file, and you can directly run it on target. In this case, it is being run on Snapdragon 8550 platform. Now that we have our quantized DLC and an optimized model, we will run it on our target platform. The SDK provides a pre-built tool called SnappyNetRun that can load a DLC model and perform inference. This tool takes a DLC model, a text file with input data paths, a path to save model inference results, and target runtime to execute the model as arguments. Please refer to the SDK documentation for more details on executing your model. Qualcomm AI Engine Direct SDK offers low-level APIs to achieve the best performance for AI workloads on Qualcomm Technologies platforms. The Qualcomm AI Engine Direct SDK supports models from frameworks such as PyTorch, TensorFlow, and ONNX. The SDK also provides offline tools to convert, quantize, optimize, and deploy models on Qualcomm Technologies hardware with acceleration. So far in this video, we discussed compiling and optimizing a pre-trained model to run on our Qualcomm Linux platform. Now, we are going to discuss how to deploy the prepared model into an AI application using Qualcomm IM SDK. The Qualcomm IM SDK is a unified SDK across Internet of Things segments. This SDK enables virtually seamless multimedia and AML application deployment. This SDK uses GStreamer, an open source multimedia framework, to expose APIs and plugins in both multimedia and machine learning domains. The GStreamer plugins enable you to develop multimedia and AML applications across various segments such as smart, connected, IP, sports, web cameras, or robotics and drones, or AML boxes. The application can be a single stream or a multi-stream multimedia, or an ML application, or a combination of all. This SDK provides a catalog of plugins that provide hardware acceleration. You can do the following things using these plugins. Run them on Qualcomm Technologies hardware or IPs, create pipelines, build and execute use cases, and optimize applications. Here are the ML plugins for pre or post-processing available within Qualcomm Intelligent Multimedia SDK. Developers can use these plugins to develop their own use cases. First, we have the pre-processing plugin QTI MLV Converter. It transforms incoming video buffers into neural network tensors while performing required format conversion and resizing. Then we have the ML inference plugins based on the model type. Next, here are the post-processing plugins depending on the use case. The classification plugin, QTI MLV Classification, performs post-processing of output tensors for classification use cases. The detection plugin, QTI MLV Detection, performs post-processing of output tensors for detection use cases. Next, we have the segmentation plugin, QTI MLV Segmentation, and that performs post-processing of output tensors for pixel-level use cases like image segmentation or depth map, etc. Finally, we have the pose plugin, QTI MLV Pose, which performs post-processing of output tensors for pose estimation use cases. Now, let's take a detailed look at the inference workflow involved in object detection on Qualcomm Linux. Live stream from a camera is captured using QTI MMF source, which is a Qualcomm GStreamer plugin. A pre-processing element such as QTI MLV converter takes the camera feed and then prepares a tensor to be input to the QTI ML Snappy plugin. The QTI ML Snappy plugin is specifically designed to interact with Qualcomm Neural Processing SDK. It is a Qualcomm Intelligent Multimedia SDK plugin, and it offers options to delegate execution of models to different hardware runtimes such as DSP, GPU, or CPU. Qualcomm Neural Processing SDK is responsible for loading and executing neural network-based AI models on the hardware. The QTI ML Snappy plugin produces an output tensor that can be parsed by post-processing plugins such as QTI MLV Detection. Once you specify the model to be used, it can be loaded, and then the plugin gains access to the model's input and output capabilities. That includes information about the number of tensors, their dimensions, and then the data types. Here, we are running the object detection application. It uses the YOLO NAS model, and inferencing is done with Qualcomm Neural Processing SDK. You can see the detection results in the green bounding boxes. Here, we see labels for objects around the house. We can also find more options for different AI models from the help section of the application. Now, let's take a closer look at the individual inferencing blocks and see how multiple elements of Qualcomm IM SDK are used. Live stream from a camera is captured using QTI QMMF source, which is a Qualcomm Intelligent Multimedia SDK plugin. The live stream input is then passed to a T element that generates multiple parallel streams, which are fed to different inferencing blocks. The QTI Composer plugin takes the results from all 4 inferencing blocks and combines them into a single stream. Finally, the Wayland plugin displays the stream coming from the composer. Each inferencing block contains 3 essential plugins: pre-processing, inferencing, and post-processing. The pre-processing plugin converts the incoming camera frames to tensors, compatible with the model input layer. The inference plugin runs the model inference on hardware accelerators. And the post-processing plugin performs parsing of the output tensors from the inference plugin. Here are the specific models used in this sample example for the 4 use cases. For object detection, the application uses YOLO NAS model with Qualcomm Neural Processing SDK for inferencing. Next, classification results that uses the Inception v3 model. Inferencing is done with Tensorflow Light plugin. For post detection, it uses PostNet MobileNet v1 model and TF-Lite inferencing. Finally, for segmentation, the application uses the DeepLab v3 ResNet50 model with Qualcomm Neural Processing SDK for inferencing. In the first AI use case, you see object detection that uses YOLO NAS model, and inferencing is done with Qualcomm Neural Processing SDK. The detections and labels are displayed in green. Next, on the top right, you can see the classification results that uses the Inception v3 model. Inferencing is done with TensorFlow Light plugin. On the bottom left, you can see the pose estimation that uses the PostNet MobileNet v1 model, and inferencing is done with the TensorFlow Light plugin. Finally, on the bottom right, we have the segmentation that uses the DeepLab v3 ResNet50 model. and inferencing is done with Qualcomm Neural Processing SDK. So as you can see, the parallel inferencing app is capable of performing 4 different use cases using 2 different inferencing plugins. In this section, we describe the process for how to integrate the developer's own model into an AI application with Qualcomm Linux platform. As shown here, there are 2 high-level paths: Qualcomm IM SDK path and AI SDK path. Qualcomm IM SDK path is further divided into 3 sections. Let's go over the first use case, namely the use case supported in Qualcomm IM SDK and model supported in Qualcomm IM SDK. These are the happy paths for developers, and they can easily deploy their models into existing reference applications in, say, approximately 15 minutes. We will go over the other paths a little bit later in this video. You can download your Qualcomm Ahub models here. First, you will select the chipset. In this case, we select the Qualcomm Q6490 chipset for Qualcomm RB3 Gen 2. We are going to walk you through using a MobileNet V2 quantized model from Qualcomm AI Hub and integrating the model into GST AI classification reference application. Open the downloaded TF Lite model with a graph viewer tool such as Netron. Click on the input node of the model to see model properties. Copy the values from the output node of the model. For example, from above figure, Q-scale is the value mentioned in quantization linear, and Q-offset is -59 at output. Developer needs to change the sign of Q-offset from the model graph. This is needed because of the implementation in the plugin. Next, you will execute the reference application by giving the constant values in the command line parameters. Take the YOLO V8 detection quantized.tflight model file as an example to execute. Take the deeplab v3 plus mobilenet underscore quantized.tflight model file as an example to execute. Earlier in the session, we explained how to export YOLO X model from Qualcomm AI Hub. You can use the custom model exported from Qualcomm AI Hub and integrate it into reference application. Continuing on with our process, let's look at the next 2 use cases in the development path. For the path in which the use case is supported in Qualcomm IM SDK but not the model, you will need to add post-processing support for the specific model into the existing Qualcomm IM SDK plugins. Qualcomm IM SDK plugins have already been covered earlier in this video. Each plugin supports post-processing of a few models. If you are bringing in a new model and the post-processing is not supported in Qualcomm IM SDK, you will need to add post-processing support. This process needs expertise of GStreamer pipelines, and it may take approximately 2 days. In the third case, you may be trying to realize a new use case with a new model that are not currently supported in Qualcomm IM SDK. In this case, you need to spend approximately a couple of weeks to implement a new plugin and add support for the model. Please note that you will be able to easily replicate the steps given in AML developer document in a few hours. But the time you see here is required when you want to implement an application of your own. If a developer chooses to use AI SDK path, they can write unit test application with AI SDK APIs, and it would normally take 1 week. This section guides you in adding model post-processing support for Qualcomm IM SDK plugin, particularly in cases where the current Qualcomm IM SDK plugin does not support post-processing for the model. In this example, we explain the required steps to add custom model post-processing to the QTI MLV detection plugin. First, you must ensure that pre-processing is supported. Next, you can add a new module for post-processing. Then you will modify a reference app with the new model. Next, you rebuild the Qualcomm Intelligent Multimedia plugin. And finally, you can rebuild the reference application. Implementing a new plugin needs good expertise in Qualcomm GStreamer. You can follow these steps for new plugins. First, you will finalize the model supported. Then you will implement the parent class. Next, you can define the source and sync capabilities. Afterwards, you can implement GStreamer standard functions. And finally, implement the modules for each model. You can follow the documentation of AI developer workflow to have a better understanding of the whole process. Detailed steps are given in the documentation to users to try a new use case, for example, super resolution plugin. That concludes Qualcomm Linux AI developer workflow. Learn more about Qualcomm Linux at the link on the screen.